There's a networking organization called the Technology Advisors Group. It meets it meets online at 8 o'clock in the morning on the last Friday of the month.
Yes.
Where we address a myriad of technology issues. This month, we're talking about new display technology.
Yeah.
You can find us at tagaustin.org, where you can sign up. It's free, and the link is published, and you can get into the meeting at 8 o'clock on the last Friday of the month, the 28th.
28th. Yes.
Thank you.
Yeah.
Thank you.
Other than the 8 o'clock, it sounds good. Can I suggest, Bob, that you put it in the chat? Yeah.
Sure.
That way, folks can.
Sure. Be glad to do that.
Yeah, great idea. Yeah, we've been partner for a long time, the TAG and Consortium networks. All right. Any other news or announcements? If not, then Louis, take it away.
Okay. Let me enlarge my slides. Okay, here we are. Welcome everybody to another or the first meeting of the year. This time we have a joint meeting with Consultants Network, live members, is it Electron Society, and probably a couple of others that I don't remember right now. Kai can probably fill in later. So here I am with the Central Texas Consultants Network. We promote the development of members' careers through professional and social networking, including publicizing members' skills and sharing potential professional opportunities, and support the IEEE Central Texas section, where all of us here are part of. And we are the local operating organization unit of IEEE, which is, of course, the big technical professional association with more than 400,000 members in more than 160 countries. We have about 200 transactions and journals and magazines and more than 18 conferences annually. So this is the slate of officers in the Consultants Network for this year. I'm Luis Basto, the chair. Jody Everett. Pardon?
The page is not turned. Your display, you may use a different display.
You cannot see it?
Yeah. I see on the side, but not. Okay, got it.
How about now?
Got it. Yeah, good. That's good.
Interesting. Always something new. Okay.
Yeah.
I'm Luis Basto, the chair. Jody Everett is the vice chair and treasurer. Bill Martino is the secretary. Kai here is the member at large, and Sergio Lieberman is the other member at large. We do have some open positions with program chair and webmaster in particular. So if anybody is interested or know anybody interested, please contact me or any one of us. This is the link to our webpage, which has the announcements of our meetings, plus the video recordings and or slides if they become available for all the current and previous meetings. Can you see it also, or is it still stuck on the officer slide?
Yeah, it got stuck. Yeah.
All right.
But next, yeah, this one. Yeah.
Something weird. Okay, so tonight's topic is the by Dr. Lawrence Larson on 17 billion wafer fab, really. And when the presentation starts, we recommend that you turn off the audio and the video just so the bandwidth runs smoothly, and you can ask questions in the chat box or later whenever Larry says, go ask. Now let me turn it over to Kai.
Okay. Hello, this is Kai Wong. tonight's meeting is a joint meeting between live member, Consortium Network, and Electron device chapters. Let me see. So that's the current live member, Central Texas section live member group rosters. I'm the current chair. Tom Green's the vice chair. Bill Martino, treasurer. Clyde Spingen, investor that you saw earlier, secretary. I'm also the program manager, and John Pell is our webmaster. And we're looking for one communication manager, try to maintain the membership communication. Our plan for this year. So we want your input and your idea on topics, speakers recommended, and maybe you can be our future speakers. And we want to have more live member participation. I think we have about 400 members in our area. That means north of along I-35 corridor, north of San Marcos and south of Waco. So the topic that we're interested in are mostly technology, 5G, 6G, IoT, AI, smart home, smart city, and finance, hobby, travel, education. We'd like to hear your story and your past contribution. Want to look into health and aging topics, and also try to understand some history on our elders, what they've done in the past, in the last 100 years, what they contribute to the electrical engineering field. There is 4 class.
Basically the same cookie, only it's all chocolate or all vanilla rather than mixed. That is, rather than each cookie having a...
Okay, somebody's talking. Okay, that's fine. Please mute yourself during the meeting. For February, we have a investment 2022 outlook by one of the local Chicago wealth management company. Speaker Jeff Kompelman. He was a speaker last year because of the power down situation in Texas last year. We have to reschedule. So hopefully this year he's going to talk on the same topic for this year's. But if you look at the stock market, I think yesterday was down, and there's a lot of ups and downs. So if you're in an investment in stock, and that may be a good topic for you. March, we'll have Dennis Ferguson. He's one of the Electron device chapter member, and he will talk about Moore's law, beyond Moore's law. April, we have a gentleman from Product Safety Society talk about product safety, and he's a consultant for TUV. A little bit housekeeping, probably Louis already done that. We like to mute your audio and turn on the video, and if you have, you can change your ID so that we can know who you are, so we can check whether we have a guest or actually member attending our meeting. And you can, please use the chat box to ask questions, and the speaker can answer later, or during the we have a Q&A session after the talk. And tonight the topic is 17 billion fab, very huge numbers, by Dr. Larson, and he's a retired professor of Texas State University. I think he's still doing part-time, as he mentioned earlier. He just done 4 hours lecture today. And he has 20 years career at Sematech. Probably a lot of you know about Sematech. It's the second consortium company based in Austin by some of the big semiconductor company in US. And now the Sematech have moved to north to New York State, but they still have small operation here. So while he was in Sematech, he was the associate director of the front end process division. If you're in the semiconductor business, you know there's a front end and a back end. Back end meaning the metal. The front end is before metal. So some of the work he's done is in a macro voltage and low energy ion implantation in Pantas. And also he worked on the vertical furnace technologies and some of the high K and metal gate technology that we're using today. He was involved in that. Sematech is basically R&D operation company for all the clients. They do it by project basis. And he's our boss here. He's the current chair of the Central Texas section of IEEE. And he also leads the student activities. And he also a faculty advisor for this TSU student branch. And he's also current chair of the Electron device chapter. Probably you already read the summary before. This the $17 billion a big investment in Central Texas area. I think the new fab will be in Taylor, Texas, only 30 miles from here. And it's a greenfield. That means they used to be farmland, so they have to put down all kind of infrastructures, road. We already have a good highway, we have a good airport close by, but everything else they have to build from ground up. So this talk will examine those cost drivers and try to estimate how they integrate. Talk about the process side and also the infrastructure side. And the process side is the EUV, the famous EUV $100 million equipment from ASML. Also the new interconnect technology, the full hole and copper interconnect and high K dielectric, and how many metal we can build to connect. And also the 300 millimeter tools, and also facility support system and all the gas and supply and power and a lot of stuff that are required to build a fab, and also need to train a lot of technicians and workers, and how to get you to a clean room, 1 ppm, 1 particle per million environment, or maybe lower than that. I don't know. So I'm out of that business for a long time. I retired in 2001. I used to be a product engineer. So I know some of those terms, but I really don't understand it, the actual working of those fab area. So I'm really glad that Dr. Larson will talk about this. So Dr. Larson, the floor is yours.
Okay, thank you. Let's see. I saw a hand up there for a while, but it looks like that's cleared out at the moment.
Yeah.
So we'll say ready to go and go for it. I want to thank our hosts.
So have you shared screen?
I'm sharing at the moment.
Okay.
I'm moving to share.
Okay, oh, good, yeah.
In fact,
Before you start, somebody raised a hand before I did not answer him. Was the person still in the raising hand mode?
No,
it's
it was me. I took it down, a mistake, sorry.
Okay, that's fine, okay.
that's perfectly all right. In fact, I will respond to hands if I see them. And if it's too pressed, go ahead and open your mic and shout.
Okay.
I'm perfectly all right to people that want to talk. And in fact, I probably do better that way. Okay, so Kai hit my resume very hard. So I'm not going to go into that particularly more. I want to thank our hosts in that, I wondered about what previously was big, the $200 million factory, but it hadn't really hit my brain that 17 billion is 2 orders of magnitude higher than that.
Mhm.
So it was actually a very enjoyable exercise to dig into it and see what I could find about what might perhaps drive that sort of thing. There we go, that's working. So this is my virtual agenda. Basically, I'm going to go into both the process trends and the factory trends that key into this. And I at least have found an answer to my satisfaction of how there could ever be such a thing as a $17 million factory. At the same time, I'm leaving lots of leeway as to the specific things. So I hope you don't expect me to explain 17, rather than, oh yeah, somewhere between 10 and 20 million or billion. That is looking like it. What I did when I got into it, I had a number of suggestions come my way and things that I read about expenses that you might have in building a factory. In fact, we had a whole group at Sematech that looked at that sort of thing. I worked next to them, but not right with them. So that will go there. And the sort of thing that comes up, the normal folk think land and buildings as the first thing that comes to mind. The technology sector points at the process equipment, the EUV, stepper, and all the other stuff. And that's a fair bit of it, to tell you the truth. We can also talk about 300 millimeter wafers, how big and expensive they are, power and the facilities. And the papers always like to get into things like salaries and taxes and all of that. I'll have comments about most of these, but to my mind, the real driver is fairly clear. Now, as just a little bit of scaling, I have this great publicity slide for Sematech. And what I'd like to point out to is simply the view, and it's one that incorporates the size of a semiconductor factory. This land that we were on is all of about 10 acres. Nothing close to what they were talking about. Had an office tower for somewhere around 400 people. And you can see here at about double the size is our Wafer Fab. This Wafer Fab was a demonstration facility full of one-of-a-kind tools. And when we did a process, it was basically one tool for each thing that you needed, and that was about it. So, and this was, say, roughly the 1/4 micron to 0.18 node where we were building and doing that work. And in the design of this particular factory, we put most of the utilities, the ultra pure water, the gases, and that sort of thing, in a separate building of their own. And of course, the air conditioning went with it. So that was piped into the building. So I put it here. I'll reference back to it.
You're still trying to load stuff up. The laptop here's, or the tablet's going. I mean, it's
I'm
just
sorry,
ridiculous.
I missed that. Okay. Didn't catch on to that. Let me go on to what I have to talk about. What I'd like to start with is simply some of the process trends over time. I will then follow. I noticed I used process trends again, but this is much more towards equipment rather than the global device thing. And then we'll move on to the factories that follow that. I use this in my classes, and it's just too concise to not include. And this is scaling. Why do we scale? Well, it's actually pretty simple. If you take up here and say that I'm going to scale the channel length by a factor S. So if S increases, the channel length goes down. You then, in pure scaling, would also scale the channel width. So this is the, all the dimensions shrink at the same time. To do that, gate oxide should also shrink, and the substrate doping to keep pace needs to go by S squared. Notice that's a multiplication. That's actually one of the issues with shrinking devices, is that the substrate doping needs to go up pretty much past where it's really capable. But if you do that, the drain current goes up by that factor of S. So you shrink the device smaller, the drain current goes up by that same factor. And this is simply using the drive equation, the transistor drive equation. If you look at the input capacitance, that also shrinks by the factor S, which means then that the maximum switching frequency, which is proportional to the drain current divided by the capacitance, actually goes up by S squared. So this is where you get that gigantic increase in speed via size shrinking. Now, at the same time, the cell area that you would put the transistor in, obviously, since that was part of the shrink, goes down by S squared. So you get more devices operating faster with more power, all by that one simple thing. Sounds like you want it. Got to have that sort of thing. And of course, you all know from history and that is what we've done. So I saw you had talks about beyond Moore's law coming. Great. I'll just say, from one of the champions of Moore's law over the decades, we're still following it. This is actually a really old slide, at least 10 years old. And the basic scaling of devices has extended and has slowed a little bit. We're talking about 5 nanometer in 15. And let me change you guys so I can see. Yeah, we thought we'd get to 3 nanometer count just past 2017. So we're only a little behind it. But that's all working, but we don't really know how to get too much farther. At the same time, a lot of things where I poke at the skeptics that are out there is that for my entire career, CMOS scaling has won. You get higher performance, you get lower cost per function, and there's some bright young engineer out there that finds a way to do it. So we're making devices that are 10 atoms across now as the gate length. It causes you to pause always, but we've always gone around those particular roadblocks. Now, where I played a lot is new materials and architectures that would go into it. And so in the sort of thing that has built devices, we went from a really commonplace planar silicon device, and we moved on towards what I put here is improved electrostatics in the Tri-Gate FET. Since we're talking Samsung, I think it's really appropriate to note that this is a hardcore structure of the most advanced devices that they do, and relatively workable to build that into designs. About the only thing I know of that's particularly troublesome is that when you have a FET, your gate width is set. This size right here, that is the gate, is 1 block. So the only way you get more drive current is lining up a bunch of FETs. But these things are so small and so powerful that it works. Moving forward, gate all around is really interesting possible stuff. Perhaps that talk coming will go into that sort of stuff. And there were even demonstrations back about 2010 or so of carbon nanotubes as gate structure. So I'm mostly pointing and saying there are ways to evolve devices and go with it. What I and we probably drove was the introduction of new materials in silicon technology. And it's actually illustrated really well by these periodic tables. When I joined the industry, it was basically silicon and the atoms around it that were those that we use. We use silicon dioxide as insulation and the gate dielectric. And to tell you the truth, not a whole lot else. Where things started to get interesting was in the 90s, where you started involving more materials. Think titanium silicide and some of the, what shall I say, sealing layers like tantalum nitride and that sort of thing. So more of the chart, the periodic chart is coming in. And basically, in my last 10 years at Sematech, the whole periodic chart basically opened up, and we found uses for those. And that's not to say that you want lots of new elements, but it's a matter of can we get better performance when we do that? Okay. So looking at the scaling that's gone on, and again, I will note that this is an old chart, but those new materials and structures have extended and have fit very well for us with the construction of super thin gate length. In fact, I saw a nice picture in the lecture I use for my semiconductor manufacturing place that had a early view of a 3 nanometer gate that looks much cleaner and beautiful. That at the same time, high performance MOSFETs with interesting channel contributions that come, and of course moving to the FinFETs and the TriFET that come. So all of this are good options and things that happen, but I'm putting it out there just to give you a vision of what's happened to the factory. So I think this is the last of those. Hey guys, look at all the stuff that's out there and coming. But this was our operating charge at the front end processes at Sematech. And so the majority of the group worked on high K and metal gate. And that was the primary target that we were doing in the first decade of the 2000s. We found a very useful sort of thing. My development group was aimed more at implant and thermal technology, where we were doing whatever we could to get very, very shallow junctions here for the higher performance. We work with other people to do high mobility materials that would fit on that. All of those extend standard planar CMOS. And we also had a group that in the 2000s built FinFETs and went for that. So that's a good target of what's coming. Now, in addition, and this will lean towards the factory, although I'm not going to build it in strongly, is simply that all of the product lines out there are separated in the processes that they use and the design targets that they aim for 3 generic areas. And we looked at that using the semiconductor drive current. Of course, we have shrinking, but then we can also work on mobility and capacitance. And well, in Sematech, we could do nothing about the chosen gate voltage, but let that be. But where I'm talking about is the manufacturers would have a design area looking for high performance. High performance maximizes the current. Who cares what everything else is? Things that we developed for that was increasing the capacitance by having high K and metal gate and lowering the VT with having low band edge work function metal electrodes that go with it. And of course, enabling gate scaling. There's also out there low power. Low active power looks and says you're going to have a low VDD. And so you really need that low VT to maintain the performance. And the issue there is the subthreshold current can and will increase. So to do that, we'd have to minimize the short channel effect and look into new device. High mobility channels drives you that way. For low standby power, lowering the subthreshold, which means change the short channel effect or address it a little bit. Also lowering Giddle does that. So the integration and once again, minimizing short channel. And of course, the low gate current, high K. All of these drove our customers and funders, I should say, to look for varied solutions that are needed. And of course, I can't go very far since we are talking about Samsung and all of that without noting that FinFET technology has hit, grabbed, and worked. And in particular for memory devices, this excellent design. Why FinFETs work is that you have a gate around at least 3 sides of the channel. This would be your channel along here. And what happens is that the efficiency of depleting the channel, when you have the field going across 3 sides of it, is markedly more efficient than when you're simply putting a potential over the top of the thing. And so these transistors turn on and turn off markedly more efficiently and basically give you a much cleaner drive than you would have in other areas. So this is an overview of what has been in terms of processing, setting the world that we live in for, what are we actually going to be trying to build with that $17 billion factory? Now I want to look at more the equipment process trends and also the process flows that come into it. This area is a big driver of the cost of the factory. So first of all, and of course it was the first thing that was mentioned to me, is the EUV lithography. And what I'm doing is using a data that came out of semiconductor engineering in a talk there. It was also, I actually found Korean references that went to it. I did not see the specific model number, but most likely the Samsung will be using the ASML NXE 3400 family devices. And here's your kicker right here. There we go. 13.5 nanometer wavelength. That just does wonders for being able to physically shrink. The bad news, and I found it on Google, amazing, is that the cost is on the order of $150 million. Now, these guys do not give out, you know, like the car people, cost for a tool. You got to dig pretty deep to get something. So I was pretty interested to find that, but that's there. Throughput, pretty good, actually, depending on the specific exposure, 135 to 160 wafers per hour, which is quite good. And a numerical aperture that we could hope for a little better, but 0.33 is what that is. Now, these numbers that I quote to you, other than the cost and throughput numbers, come as entries into the Raleigh criteria for resolution of far-field litho, which is detailed up here. Basically comes out to a fudge factor, K, with no specific physical meaning. It is proportional to the wavelength and divided by the numerical aperture. So to get small resolution, you want to reduce K, you want to reduce lambda, the wavelength, and you want to increase the numerical aperture. Oh, come on, advance for me. So, numerical aperture is literally an analog of the size of the aperture that the light comes through to be used. And that calls for large lenses in an optical sense. Interestingly, there is an intermediate solution, in fact, developed by Sematech with the supplier, using immersion. Because the index of refraction of water is larger than that of air, you can increase that numerical aperture by increasing the index of refraction. And in fact, a mid category of that actually was a pretty good linkage. And there's all sorts of tricks for decreasing K, but it's hard to do. And this will show you how old my slides are. Decreasing the wavelength, it's not easy because the industry still insists on 193. We were stuck there for a long time. And interestingly, the steps beyond that were tough until you got there. Now, just to let you know what we're talking about. Back when we were actively working with mercury type of wavelengths, picking different mercury lines, which, by the way, is most of the older lithography. Come on, where's my thing? There it is. Yeah, there we go. We were dealing with wavelengths in the optical area. The largest line, the healthier line of mercury is somewhere about here, and they did push it down significantly. But I note to you, they're all right here in the full electromagnetic spectrum wave. So that'll show you just how big it is. So radio guys, you operate out there. X-rays in the lab are here, and gamma radiation is there. And here's our EUV at 13.5. What a jump. So you can imagine going back here, dropping lambda from 183 nanometers down to 13 is a factor of 10 in resolution. If you can do it, boy, we want it. Do I need to go back and show you the price tag? No, that's pretty serious. Anyway, I did also have deep in my Sematech stuff this physical description that sort of shows you where we're coming from. 248 is our quarter micron or micron type of resolution. As you can see here, it's not all that good, Notice the numerical aperture of 0.7. As we go to 193, which is an argon fluoride laser, numerical aperture stays about 0.7. I think you can visibly see quite a bit of improvement of resolution. Let's see, this is all 193. The big competitors 15 years ago were a fluorine laser, which gave out 157, and a markedly good numerical aperture. So you can see here pretty good performance. And taking 193 and doing an immersion with that. If you remember, that gives you like a 50% increase in the numerical aperture. So there you see a spectacular numerical aperture and a really good resolution. But there we are, bad numerical aperture, but 13.5 nanometers gives you a very high resolution. And that, my friends, is what's enabling 5, 7, and 3 nanometer type of devices. Now, notice that we're talking 9, 5, 7, 3 nanometers with 13.5 nanometer light. That means that there's a lot more tricks involved that go with the making of the mask and multi-layer exposures and things like that, that give you that sub-frequency, sub-wavelength exposure. But still, that's the best game in town. So, EUV is the clear winner. It's the clear winner in performance, and it's the clear winner in expense. And as all of you in business know, performance and getting out the good product with a good margin on it, that outdoes expense anytime. Now, I will note to you that EUV is not the only expensive large tech-advanced process tool. Also, as per my discussions that we had before, right, when we're talking about processes that come in, I dealt with ion implantation. And I know for a fact that 10 years ago, they were on the $5 million range. So they've probably gone up. You need to have ALD, atomic layer deposition, for high K gates, metal depositions for metal gate, multi different materials, copper itself, and chem mechanical planarization. All of these are expensive, large, high-tech process tools. Okay, well, going into those, of course, my big deal is ion implant. When I joined, we were, putting a implant into the process or developing one. But after VT and then subcollector, it just exploded in terms of what you can do. The process development folks working with good simulations and build it have added implantation after implantation for things that are needed. So just moving through, of course, we have an LDD implant, which is really shallow. 500 angstroms deep was our target, and middling density to high in the contact area. But channel engineering was a big technology that people were going. And you would have retrograde channel up close to seal the channel in. You'd have punch through and pocket implants to make sure the leakage currents were minimal. Then we would have retrograde wells to tune the fields and the amount of leakage that you might get on both that would seal in these. By the time you get to where we're headed, there are 9 to 10 different implants. No big deal. Implanters are good for doing lots of stuff and that. But as I go into the processes themselves, that means it gets used, and you may need a separate implanter for each one of them. You hear the cost rolling. I threw this in just to illustrate that high K and metal gate is absolutely necessary. And it's one of the cooler things that to show a CV curve. And you can see that the one on the polysilicon electrode is rather flat and barely turns up on positive voltage side. And the metal gate, even though it's simply a tantalum nitride aluminum electrode, is nice and crisp in that, with a clean, effective oxide thickness of 15 angstroms. So with high K and metal gate, you can pass that 20 angstrom limit for regular, I shouldn't say regular because that's silicon oxide type of oxides, really high quality, but the CV just stretched for that. So you need high K, you need metal gate. Okay, no big deal. We've learned how to do that. High K does, of course, we have to learn how to deposit hafnium oxides, different kinds, depending on where you are for that. And metal gate is something that people don't talk about a whole lot, but it's very cool in that, of course, it lets you implement your technologies, but the depletion, there's a real issue with depletion of polysilicon gate. Very low resistance, no boron penetration, and you can design capability with high K. So you want it that way. Issues with it is we were so spoiled using silicon because the work functions would always match or be close. Well, once you put different metals in, then the work functions all over the place for that. And so basically you end up needing two different metals that would go, and all of that compatibility issues that go with other devices. So I've gone on for quite a while with respect to the processes. And by the way, that's because that's the stuff I know and can really get into. The effect it has is that the process flows have been growing asymptotically. Well engineering that I showed you in the implants, high K materials, 2 metal gates. I haven't even talked about copper itself. And you've seen in many places, people advertising that they're doing 6 to 10 metal layers. Each of those is additional process steps that have to be carried out and built in. So what I see, and interestingly, this is over my career and probably a fair bit of yours, as it were. When I started work in the 70s, there was 10 to 15 process steps, which were on a 3x5 card, which was taped to the top of the 3 or 4 inch wafer box. And that's what you did. As we moved along, somewhere about 1 micron CMOS, it was up to about 50 steps. So that'd have to be on a long sheet, like an 8x10 sheet of paper or something of that sort. And yes, that was before all the cleanliness stuff. So yeah, you'd have the paper sheet and people would sign an initial that we did it. When I was at Sematech, we were doing a 1/4 micron process, and that had 120 steps on a computer. And just to show you, I walked away with one of those. Now, I'm not going to lecture about this, although I do to my students, but more so, in fact, of this. But I'll point to it right now and just say, every one of these steps is either a different process or a different tool that is used as you build your process. So, well, that was my target. going beyond, as a basic thing, you need about 7 steps for a litho loop for a well engineering layer. And you need about 12 steps for the litho loop that is a metal layer. So even though I don't have the processes of this kind, you can expect that they increased by at least those. The process itself has expanded markedly. So this is here because I'll actually use that a bit later, but not get into it. I want to turn a little bit. Actually, I see, I'll take a little breath and see if there's any hands up or microphones of people just itching. Any comments or questions? Okay, well, I'll go on then and hit you with the hard stuff. Share go. Because now I want to talk about the factory trends itself. And this is where I started looking at what's been publicized about the factory. Because one of the first things that people mention to me is the land and the buildings that come to it. And so I want to sort of refer to you and say, hey, what about this 17 billion thing? As I went into that and took a look, basically what I found in the American Statesman, and actually several other ones. By the way, I have references down here on what they are. The land purchase that they actually purchased was 1,200 acres. Well, the average Williamson County price per acre, and I kind of doubt that Samsung would pay average, but let it be as it is. The estimate then is they would get that land for $6.3 million. Well, I know that's enough to stagger you or I. However, the factor of 10 is off by 1,000. So this is just 0.5% of the entire cost goes into land. So as I read on, I started learning stuff. And Sematech is a consultancy firm that looks into buildings and stuff. And they actually had a very well-written place. In fact, if you want to dig deeper, you may want to look into this reference on that. And they estimated that the $17 billion cost was about $5 billion for land and buildings, and about $10 billion for the semiconductor process equipment. That made good sense. And in fact, they quoted a Stanford study, I think, that went into a little bit of detail about the semiconductor process equipment, of how that all fit together. So to make some sense about the building cost, construction cost is another thing you don't get without a bid. But interestingly, this is a pretty large consultancy on building all sorts of buildings. And they had a global average per square foot for high-tech laboratories. Well, that makes some good sense. The number I got of the 6 million square feet at $635 per square foot for a high-tech lab gave $3.8 billion. So what that is, it means that a large part of it, 20 to 30% of the 17 billion, is clean room and facilities. I was actually really interested in the power cost that would go into feeding this puppy. But that at least says, okay, we've got something here that is of the order of magnitude billions of dollars, and also fits pretty well with other estimates that are out there. So building a clean room is a fair bit of that. Then somewhere about in here, the light went on. And I said, okay, what about the equipment? Now, this is where I was wrong. You may not hear speakers say that very often, but I thought that 300 millimeter plants were pretty rare. And that I know that the tool suppliers have to put in the full engineering rework on their tools to raise the size. And so I was expecting that the development cost of that would be put over the same base. But actually, no, I don't have that there. I was going to put the reference in there. But actually, I found out that the number of 300 millimeter fabs for this middling period in their introduction is following about the same curve as the 200 millimeter plants. And so you can expect that the development and production costs roll pretty much through. But I was able to go through my references and find nominal numbers for the different tools. And interestingly, I found a real good number for the FSI spin wet cleaner of 3.5 million, but it actually had a pretty low throughput. So somewhere about here is where the light went on for me, at least with respect to this. Because I will admit to you that most of my work was in development fabs and first run type of stuff. So that picture I showed you of the Sematech fab has pretty much a minimum volume fab, but sort of like one tool of each kind. And as we work through it, sort of standard for that kind of fab is that you expect to be a successful semiconductor company. That to do, the tool is going to have to do about 20 wafers per hour at a minimum. And you can take a one-of-a-kinder of that and do a first intro fab that does about 2,000 wafer starts a week. So that was my picture of a fab. And so as I dealt with this industrial engineering, I was sort of looking at this sort of area, in particular saying that one tool going down stops the whole line. And so there's good practice of cross-qualification and multiple tools per step and all sorts of stuff like that. This is where the light turns on, because that same production from an Antec estimated that Samsung is planning for 70 to 100K wafer starts per month. This is 100,000. This is 2,000. Whoa, something. So it's 10x the minimum tool set. Not only that, but I found Samsung publications saying that in 2015, they had in fact, it may have been past 15, it might have been 18. They had a capacity of 300 million 8-inch wafer starts per month, and they planned to triple that by 2026. That was by building one plant, and we know where the one plant is, and expanding 5. So what I'm seeing from that, and when I converted from 200 millimeter wafer starts to 300 millimeter wafer starts, I got that that single plant could be doing as high as 300K wafer starts. It's not just the tool price, it's the volume. In fact, I watched a YouTube video last week for my class for Intel's Fab 42, which is another big guy. In fact, that was where an Antec did their 100K, and that's a monster factory. It literally is 10 times the size of what I showed you. And so, you know, I had that process flow. I figured, let's do a little work, just to see where it is. So I used the Sematech flow as an estimator. I added some more steps for well engineering. I put 4 layers of metal. I actually, because it's the business I was in, have a pretty good idea about cost and throughput for each tool. And then I varied the volume as per those estimates and quotes. And what did I find? Well, here is a plot of cost versus volume that came for different volumes. I will note to you that I started at 100,000 wafer starts per month. And the total I had for my flow was about $11 billion. That was split up as the 3.8 billion for the clean room, and a total of about 7 billion for all of the process equipment. Of those, surprise, surprise, the litho, the ASML, was the biggest contributor. Now, thinking about 17 billion, I then drove it up in terms of the wafer starts. And I hit the 17 billion number here, about 220,000 wafer starts. Since then, I've thought of all sorts of extra things I could put into it. But at a certain point, my point is made, to my mind, is that a very large, complicated flow, so much volume that they not only could, but should have multiple machines per step. By the way, at even 100,000, there was no step in the process that only had a single process tool that could do that volume. That's not too surprising. Just to note, number of tools per volume. Now that came a little more. Well, in fact, I should go back and note, sadly, and this is probably why I never got a big salary, implant and wet decks were pretty much a trivial cost compared to the other stuff, even though they were big contributors. I also looked at number of tools per volume, and that was kind of interesting because the litho ran from a low of about 30 of those $150 million behemoths up to almost 60. The implanters, which are big and expensive, went from 18 up to just short of 40. And I'd like you to note that because their processing capability changes, this curve jumps at different points. The litho is actually pretty good. And here, for the wet decks, you just flood the thing with those. Wet decks are sort of interesting because they have a chemical process that it's basically gonna take as long as it's gonna take. And so you just need more chambers. This is real conductive for that sort of thing to do that, but it's a large one. Now, do not try to build silicon on this. This is an argument that, it's clearly the process flow and the volume that drives the $17 billion. And the ratio, as said by Anantech, really fits pretty well. 5 billion for the clean room and a little bit for the buildings and the roads and all that sort of stuff, but it's really not large as things go. And then 10 to $12 billion for process equipment. So that's my answer. I see a number of things came up in the chat, but we can chat about it. Land, I say, is no. 300 millimeter wafers, I never really looked into very far, but basically when the process is flowing, each tool has a box in it, and that cost is small. Power and facilities, I'm interested in, just because that goes. Salaries and taxes, are incremental costs that go with it. And the big is process equipment to the order of 12 million roughly. Well, excuse me. Process equipment and volume to the order of about 12 million. And the clean room is about 5 billion as it goes. So that's my end. And hopefully it's a good discussion about where it sits. I'll take a look at the chat now and see where things are. You are, of course, perfectly okay to say things. Let's see, Kai says Samsung has the full of state, county, and city. That goes. Yeah, Sematech was to Behram. Definitely Sematech was a research lab. And in fact, that's the thing that really key for me. That major difference was an eye-opener for me, that there's all sorts of scale that comes into it in terms of the volume, and definitely in an industrial engineering sense, all sorts of things we could go. Alan, I like your comment. 3 miles from ERCOT's command center. I do not think that's coincidence, because believe me, power is going to be a big deal. And Behram asks how much of these 17 billion will be left for these. Well, in fact, it's for all processing after the monies are spent for building construction. Well, actually, I thought I argued there fairly decently that 5 to 6 billion is the building construction, and the other 12 will be processing equipment. Too much. How much of the money comes from the government? I don't know. If any of you have a clue, they've certainly gotten some massive tax breaks. However, I will note to you that, you know, it's not a bad idea to give them a tax break to get this economic engine in the area, because believe me, the secondary money flow is going to be spectacular that goes with it. So I actually think the government tax breaks they got is not a bad idea. Okay, and that's most of the questions and comments that come in. Oh, okay, Jerry came in and said, is the wafer the end product of the plant, or are there processing steps to break these down into sub-products? The correct answer is I don't know. Because certainly in plants that I've worked, the packaging side or the initial test and sort would break it down to the die level. Packaging in general has been shipped off to the Far East, and I haven't heard about any packaging type of stuff. But test and sort could well be in that area, and cutting it into die would be a part of that most likely. Let's see, and Kai says, how many process and device engineers do they need to run 3 shifts? A bunch. Again, the truthful one is I don't know.
Okay.
But when you have, let's say, 250 tools, in fact, it was more than 250 tools. It was multiples of that. There would be a staff of process engineers that is pretty serious to run that.
Yeah.
I'm trying to remember, does anybody remember the employment numbers that came out? Because I didn't really pay a lot of attention to that, but it was in the multiple thousands.
Well, my understanding is they have 2 fabs in the current plan. So probably they need to transfer some over there and then train a lot more. So I think there will be a training recruiting and training time, and are they from green engineer to seasoned engineer, or they kind of steal from Intel or some other place?
Yeah, they, in fact, not about the engineer side, but I ran across some very interesting information about Intel's Fab 42 in Arizona. And that is the one that was quoted for the 100,000 wafer size, and gave some of the initial 40 litho tools as the kind of target. And what I noticed with that is that they had tied together all of the Arizona fabs so that they could actually link capability and engineering coverage, as it were, and all of that throughout those lines. So you had basically a super mega fab by tying a mega fab into those other small ones that are the other side. The Internet of Things is hitting us big time. These plants are building up to just put out an amazing number of devices that we use in just about anything that's to the side. It's no longer just the desktop computer.
But I think the Internet of Things may not need the most advanced technology, right? Only computing or high performance or the AI may need.
Oh yeah, sure, yeah. My coffee pot.
Yeah,
no way.
Right.
It can do with the 486 just fine.
Yeah, you can buy 50 cents MCU.
Yeah, at the same time, the advanced technologies, maybe a lower part of that, can build the same device to almost high precision and shrunk almost out of existence. I actually got a hand with that with my microcontroller class that I taught last year, and the Raspberry Pi.
Yes.
And the Arduinos. Those things, the Raspberry Pi is way more advanced than the desktops that we had 5 years ago, and is all in a package that's, a 1/2 inch by 3 inches by 4 inches. So it's all shrunk and can use some amazing technology because it's out there. Not to say that they will, but they can. Oh, okay. I got a big comment. Alan says, regarding building costs, when I was in graduate school in the mid-'80s, we had a guy from TI to speak to our class about new fab construction. And I believe TI was planning their first $1 billion fab, and he told us that building represented 4% of the total cost. And he doesn't think that included clean room expenses.
Yeah, his point in telling us that was it was all equipment.
Yeah.
pretty much what you were saying.
Yeah.
He didn't go into details, but he basically just said the building, the parking lots, the office space, all of that was 4% of the total cost. And then the rest of it, 96% of it was the semiconductor equipment. And I think he counted the clean room as semiconductor equipment.
Okay.
Yeah.
That would fit very well. It'd be somewhat equivalent to my noting that the cost of the property in Williamson County was only $7 million. Wrong order of magnitude.
So I see a hand from Ravi. Can you unmute yourself and speak?
No, I didn't have my hand up. I'm okay.
Oh, okay, okay.
Larry, that was a good talk. I hope you can give my graduate student similar talk in a couple of weeks.
Oh, okay. I'll happily just ship it over to you if you like.
Yep, thank.
Yeah, I think you can send the slide to me. I post it in our website.
Okay. I do that by shipping them to you too?
Yeah.
Okay.
How big's the file? You have a lot of pictures.
There's a lot of pictures there. I don't actually know.
Okay.
If that is of concern, I will check and let you know before I send it.
Yeah, you either do that or put in the Google Drive. We can pick it up.
Okay, yeah, we'll talk about it.
Mhm.
Okay, Ralph says Intel Corporation spent $40 billion to build Fab 12 in Chandler, and it was paid off in 2 years using accelerated depreciation. Amen.
Yeah.
That's the way it works.
Yes. Right.
More so, just the product that moves through there would put 40 billion just becomes a small percentage. Crazy numbers though.
Yes. So just like the old days. So maybe in 2025 we find we have overcapacity. So everybody building new fabs.
Yes, indeed, and we'll be firing all those engineers.
Yes.
Well, we won't. I'm going to be retired. I think you too, Kai.
Yeah. Yeah. Well, I am already. Yes.
Don't forget that TSMC is building this big super fab in Arizona pretty soon.
Yeah. Well, they all announced 2024 phase into production. Very aggressive. Both
That's right.
TSMC and Intel.
Well, there goes the property prices.
Yeah, if you add together all the volume that's just in those 3 fabs that have been announced and are looking very seriously, once again, it's just an astounding number. There's nothing more expensive than a factory that's not being used.
Yeah. So
Good comment, Barham.
yeah. I don't think they have that thought at that time.
Well, they'll
You
probably
face
be
it.
using an accelerated depreciation type of scheme like Intel did,
Yes.
at which point inflation most likely is not an issue. But yeah, it's out there.
Mhm. So somebody earlier talked about the power. So I think last year we already have power. The Samsung got shut down for 1 week in Austin because the winter problem. Maybe actually they shut down for twice. One in February, one in another time. So power could be a major problem. But hopefully we'll resolve that in 2 years. From ERCOT and some other better support system.
Yeah, one thing I heard about that is, they lost power for 5 or 6 days, but 3 weeks after that, I heard just from someone in my company that they had not restarted yet. So they were actually offline for a number of weeks. And I was wondering if Lawrence or somebody else might give some comment about what it is that takes so long to start back up after you've lost power. I mean, do they have to recalibrate all the machines, or is it cleaning, or what? Why can't they just start things back up when the power comes back on?
Oh, that doesn't work at all. Well, there's all sorts of things that take a while to get correct. From my own experience with furnaces, which are probably some of the most minor of that sort of thing, they are normally idle at 500 to 600 C, and then driven up from there. And to get to where that is there and stable takes probably a day. That's one of the easy ones.
Yeah.
What I'm thinking about is the lithography as probably one of the big ones. And the sensitivity of the mass and the alignment to thermal disturbance is extreme. So they literally, the process chamber lives inside of an area that is controlled to, I think, better than 1/10 of a degree Fahrenheit. And every part of the mask and the tooling that handles the wafer and the beam has to be kept that precise. That I have no problem thinking it would take a week for it to attain stability and then demonstrate, actually test it. On a more mundane level, the amount of ultra clean gases and water that are used, basically once power goes down on those, it's no longer ultra clean. In fact, I'm always amused at the cities and states that require processing of the semiconductor plant effluent, because as a general statement, the water coming out of the plant is cleaner than the water that's delivered to it. So, but that's test, not politics. And so I know I didn't make anything there, but I'll just, sort of point to you and wave my hands broadly that startup of what is basically a significantly large precision instrument, place after place process line. Every step has to be brought back, stabilized, calibrated, and qualified, basically, to run again. And even 2 weeks strikes me as short. I know I left Santa Clara in '89, and it took 3 months to bring National Semiconductor back online after the earthquake. That was a combination of both the physical motion that took place and the fact that all the facilities went down. Not a happy time.
Another consideration is I wonder how much of their wafers have to be scrapped. I mean, some of them probably cannot be brought. I mean, you can't just stop in the middle and bring it back in 2 weeks and hope everything continue running, right? Depending on which step, I guess. I would think there's some loss in there too.
There's got to be. Definitely anything that was in a machine, dead meat. Wafers that are safely offline, some sort of storage, queued for the next process step, maybe they're savable. But there would be a whole lot of product engineers sweating for a month at least to see how that first material worked out. Okay, it looks pretty quiet, Kai, and we're losing people.
Yeah, that's a great presentation, Larry. I think everybody learned something, I hope.
Hopefully, hopefully.
Yeah. Well, so we can stay and talk, or maybe anybody have any other questions or talk about other topics?
Yeah, that's right.
We still have time. So I think, yeah, go ahead, Bob. Unmute yourself.
No, I was just gonna, that was just my wave saying I had nothing to say and not too much to do. I was gonna get on with my evening. Thank you. Thank you
Fair
very
enough.
much for a great story. Appreciate it.
Yes,
Yeah. Well, bring your stories to this forum. We'd love to have it.
yes.
Well, looks like people are leaving, and if we don't have any more questions, we can conclude this meeting.
All right. Okay. Thank you,
All
Dr.
right,
Larson.
thank you all.
Yeah.
Kai, Lewis, I'll see you Saturday as appropriate.
Oh, yes,
Thank you,
yes.
yes.
Okay. All right.
We'll go
Okay,
from
bye,
there.
everybody.
Bill wants you to approve our budget.
Yes.
Yes.
Yeah.
Thank you.
Okay, take care, everybody. I'll go off to it.
Okay,
Thank
good night.
you.
Okay, good night.
Bye, everyone.
Okay, stay tuned. We have some more good program coming. Bye.